Now that we've gone through the explicit details of a model that has a phase transition, let's step back and discuss some of the general features and qualitative facts about phase transitions and phase diagrams. We'll start by recalling what the phase diagram would look like for a van der Waals model. We have an envelope here that separates the pure states from the mixtures. But inside of this envelope, we know that there was a region of mechanical instability on the inside, and a region of metastability near the edges. So I'll just write meta with a period after it for metastable region in blue. And outside of this phase diagram on the left was liquid with an L, and outside on the right was gas with a G. When we go on this phase diagram to draw a line of constant temperature, an isotherm, in the liquid region the isotherm is very steep, comes down. Once it gets to the mixture region, we transition across the mixture at some constant pressure, which is called the vapor pressure for that temperature isotherm. And then once we get to the gas region, we go out into the pure gas region. So that's what an isotherm looks like. The critical isotherm is the isotherm that goes through this critical point, and that isotherm never has any transition region. The system is in a pure state the entire time. So just at the critical pressure here, it has a zero slope, but then it goes up and starts looking maybe more like a liquid. So anything really that's below this critical isotherm and to the left of the mixture envelope is clearly a liquid. And anything that is below this critical isotherm and on the right side of the envelope is clearly a gas. Anything that is above this isotherm is technically called a supercritical fluid, where it doesn't have a phase transition between gas and liquid. We can go continuously between them, and there's just a continuous variation of density. So that's what the phase diagram would look like for a typical liquid to gas transition, and we get this from the van der Waals model. One thing always to remember is that from the van der Waals model, we know that hidden within here is kind of this, cubic shape with a local max and minimum, and the unstable region is where it's sloping up, and the metastable region is where it's sloping down, but still not the lowest possible free energy. So there's another type of phase plot we can make for this system. It is a phase plot of pressure versus temperature. And what this phase diagram looks like is a little bit different from this. So let's think about it. At the critical pressure and the critical temperature, we have the critical point right there. So that's a point that appears on both phase diagrams. And up here, we're in the supercritical region. So anywhere above TC is in this supercritical region where there's no definite phase transition. And also, if we are above the critical pressure, right, if we're looking at a pressure that's above the critical pressure, then we will not have a phase transition as we change temperatures either. So the supercritical region is really this entire area over here on the top, on the right, and on the top right. So what happens in between this region here where the phase transition actually exists? Well, TC is a critical temperature, and as we go to lower temperatures, then we see the vapor pressure going lower along with it. So there's some sort of line here, a relationship between the vapor pressure at a given temperature. So for example, this second green isotherm here, the first one I drew, but the second one down from the top, this is some certain temperature and it has a vapor pressure. So that would be a point that we can draw right there. So the phase transition would happen if we were like compressing it, from a low pressure and increasing the pressure to up to a higher pressure. This whole mixture region here would happen all at this point. So at low pressure, we are down here. Low pressure is over here, so this is the gas region. And a high pressure is up here, so this is the liquid region. Now, what we're really seeing on this graph is more like we're looking from a perspective on this PV plot. We're looking at it from the side. We're looking at it from the side. So we see this envelope of flat lines here comes up to a point and then terminates like that. So what we're seeing here is from the side. If we look from this way, what we're seeing here is a variation of pressure with temperature, and then an end to that line. So one way to get a better understanding of this kind of phase plot is to think maybe of what volume we would observe at each point. Okay, so looking at the PV diagram here, at a specific pressure, at a certain pressure, so like here along this vapor pressure line here, when we are at low temperature, we're going to be in the liquid regime, and that's going to have a lower volume. So we'll have low volume up on this side of the transition line, and in the gas region, we'll have high volume. So what we are really depicting along this line of phase transition here is a discontinuity in the volume. There's like a cliff here. We have high volume up here, right? High volume up here, and then low volume down here, and there's this vertical drop off between those 2 points. So sometimes I even try to draw this like there's maybe like some sort of perspective drawing on here, though this isn't really what's supposed to be shown by this PV plot. But if we maybe just took this graph and tilted it a little bit, then we would expose this cliff that's between the high volume and the low volume regions. So as we come this way, we come up, we have high volume gas, then we drop down, we stay at this a point on this line the entire time during the phase transition until we get down to this low volume region. Now what happens on this graph at the critical point is the difference in volume between just to the left and just to the right of this phase transition line, the difference in volume shrinks down to 0 at that critical point. So we're coming up, up to there, boop, the difference in volume goes away, the difference in volume goes away at that point. And out here, the volume changes in a continuous manner. So it's almost like we've got, on this plot, it's like we've got a rip or something that started in the paper. So we've got this rip like that. We've got a high region on the bottom right, a low region on the top left, but then a continuous circle could go around counterclockwise on the page like this and not ever have a discontinuous change in volume. Now let's look at a different type of system that also exhibits a phase transition behavior, but it's not the kind of phase transition you might be familiar with. What we're going to do next is make a phase diagram for a mixture. Now, way back in chapter 2, we had a few small discussions about how to approximate a liquid mixture. So this is going to be a liquid mixture. And a very simple model was proposed called the simple mixing. And the simple mixing model is where you imagine that there are, within your liquid there is n total spots where molecules could be, and then NA of them are chosen to be holding molecule A, and the rest of them, NB, are chosen to be holding molecule B. So you just have a multiplicity which is based on the number of permutations, where you can choose which slots get molecule A and which slots get B. So we did some exercises on that, and turned out that we did a problem actually that solved for the entropy in this system, and it was minus NK times the quantity x log x plus 1 minus x log 1 minus x. And this was where x equals the fraction of molecules that are of type A. So fraction of A to the total is what x equals. So this was the entropy of that model. And we're going to look at the possibility of a phase transition here. But first we have to get an expression for one of the free energies. So what's the appropriate energy to use here? If we're talking about a mixture in a liquid, what can we change? Well, we can change the composition of the mixture, so we can have a certain amount of molecules of one type and a certain amount of another type, so we can control x by basically how much is dumped into this beaker containing the mixture. We can also vary the pressure, and we can vary the temperature. Since we've got a simple expression for the entropy here, we're going to approach this from the perspective of varying the temperature. So we're talking about a free energy that depends on temperature, and that depends on the concentration or the numbers of particles. So we could choose either Helmholtz energy or Gibbs energy if we just need a dependence on temperature. But since this is supposed to represent a mixture of liquids just kind of sitting in a beaker, then in all likelihood this is going to be an experiment that's carried out at constant pressure. So we're going to go with the Gibbs for energy here because of the constant pressure and the variable temperature. So we have an expression for the entropy. And the relationship between the Gibbs energy and the entropy is that derivative of G with respect to temperature is negative entropy. So this gives me an entropy here which doesn't depend on temperature at all, right? It's in terms of particles. Particle numbers basically is all that's in here. X is just a variety of particle number. So I can integrate this quite easily without worrying about any of these things depending on temperature, because they're depending on number of particles, which is a natural variable already. So I'll get positive kT, right, because minus and a minus, a positive kT times x log x plus 1 minus x log 1 minus x. And then since this was a differential equation of a partial derivative with respect to t, I am still able to add on any other function of variables besides t, right? So pressure, concentration can still appear in here because as long as there's not a t, it'll work out correctly. And this could also depend on the total number of particles in the system. So you could also write this part as pressure Na and Nb, and that's fine too. But pressure X and N is better for our purposes since this part is already in terms of X, the concentration. Okay, so the part here is due to a simple mixture, and what do we interpret for this part? Well, we'll ignore the dependence on pressure since we weren't really depending on changing the pressure of the substance anyway, but there might be some dependence here on the concentration, and this is going to represent an addition or subtraction to the Gibbs free energy based on the concentration of molecule A. All right, so there's a couple of possibilities here. One of them is just, well, first of all, there's one thing that's not possible, and that is for this to have some non-trivial dependence on the number of particles n. So we've got an extensive quantity here, we've just got one extensive, and it only has one extensive argument, so it must be equal to n times some function of the intensive arguments. So there's two possibilities here. We've got an n out front, and then we've got perhaps just a favorability towards one molecule or the other, right? Perhaps one molecule just has naturally lower energy to keep it around, a lower chemical potential, so it might just have a term that's we would represent that by a term that's linear in X. So if it's high concentration of A, it just takes more energy to get that to happen than a high concentration in B. So what we'll do here is we'll represent that by a chemical potential, mu D, times X. So we're just going for qualitative features here. So this mu sub D kind of represents a chemical potential difference between particle A and particle B. It's not so important what its value is. It could be positive or negative, but this term just represents then a favorability towards one molecule versus the other. We're still able to put as many of each kind as we want into the system, but we might pay a price in Gibbs energy for having that arrangement. The second term here is going to be an additional energy to the Gibbs free energy, so an energy cost, and it depends on the product of X and 1 minus X. So what this is really representing here is the product of Na and Nb. And if Na and Nb are close to each other, then this X is close to 1/2, and this form here would be maximized. So if the lambda value is positive, then this is an additional Gibbs free energy that comes from the particles really not liking to be close together. They would rather be in a concentration where one of these x's or the 1 minus x is very low, right? So we take this term to represent an interaction between the molecules. If lambda is positive, then they repel each other. They don't like to share concentrations. And if lambda is negative, then they attract each other and they'd rather be together. Usually for substances, this lambda parameter does have a positive value. Note that the mu d and the lambda would both just have units of energy then, since g is an energy, n is a moles or a molecule number, and x is dimensionless. But we can, in fact, match up these two parameters to values for real mixtures depending on what two liquids are mixed. Okay, so we'll take this as our starting point. We'll write it as Gibbs free energy over n will be equal to kT times x log x plus 1 minus x log 1 minus x. And then we've got a plus mu difference times x and plus this lambda interaction term. So that's our model for the Gibbs free energy of this mixture of two liquids. So what we'll do here to decide if this has a phase transition or not is let's first just look at each of the terms and see what they do to the overall energy as a function of x. So remember that x is the concentration of one species in the mixture. And first let's draw this term here in red. So x log x what does this really look like? Well, logarithm is negative and it goes up. And we got the x multiplying there. So this goes to 0 in the limit of x equals 0. And its slope at the origin, right? If you look at just this term, its slope at the origin would be kind of logarithm of x plus 1, basically, if you take the derivative of this. So the logarithm of x at the origin is a negative infinity. So this slopes down, this term here slopes down very drastically from 0. This thing over here, the second term, does the same thing near x equals 1. And this is symmetric around x equals 1/2, right? If you swap the x's and the 1 minus x's for each other, you get the same thing. So for this red thing here, we get this curve, which looks qualitatively like this. It's a downwards, sort of a downwards curve with a very steep slope at the edges coming up to 0. The other thing about this curve is it's multiplied by the temperature. So if we raise or lower the temperature, then this curve will go up. If the temperature is raised, it will go down if the temperature is lowered. All right. Next term here, mu dx. That's pretty simple. That's just a line. All right, and you can see here why we said this might be related to a difference in the chemical potentials for each species. If you're at x equals 1, then you're 100% particle A. You would end up with the chemical potential of particle A. If you're at 0% particle A, 100% particle B, then you get a chemical potential of particle B. It's not important to shift this up or down because that would just be a constant that changes where 0 is. Okay, lastly we'll look at this lambda term here, lambda times x times 1 minus x. So this is a parabola, right? It's quadratic in x, and it's 0 at each end, and it's always positive. So that means it basically must look something like this. And if we change the lambda value, then this thing will stretch out right? But one important thing about this green curve is that the slope at 0 and the slope at 1 is finite, right? You just take the derivative of this, right? It's going to come out to like lambda, 2 lambda or something, right? So plus 2 lambda here, minus 2 lambda over there. So we've got a finite slope for the green and blue curves at the origin, but an infinite negative slope for the red curve here, an infinite positive slope for the red curve here. So that means when we get close to x equals 0 or close to x equals 1, we're always going to have some amount of downward motion to the total value of g, even if we end up getting some, net positive from the addition of the green curve. So let's look at the total value of the Gibbs free energy and then for this kind of plot. So we would start off going steeply down. Then maybe at some point here these would kind of equal out. We would be closer to the green curve then. And then down here and then back up. We always have this upward tick at the ends because the slope of the red curve is infinite. So this is what our G over N would look like qualitatively for this kind of picture. Of course, as you change the temperature and the value of lambda, the shape of this might change. To be dominated to look more like the red one, or dominated to look more like the green one, or somewhere in between. But that's the general idea. So let's see how this can generate a phase transition. Over here on the right, I'm going to keep track. What I'm going to draw is a phase plot, a phase diagram, with concentration between 0 and 1 on the x-axis and temperature on the y-axis. So I'm not going to draw any really graphs over here, but I'm going to indicate areas. Then on the left side over here, I'm going to draw an example of what the Gibbs free energy might look like as a function of x between 0 and 1 for some specific temperature. So we'll mark out a series of temperatures here. So what I'm doing more or less is I've got an axis here for Gibbs free energy, but then I'm drawing a set of staggered graphs here with offsets based on what temperature that is at. Okay, so let's start off with a graph at high temperature. At high temperature, remember, this red part is really dominant, so we're just going to have something that basically bows down. And there's nothing really interesting going on over here. We're going to have, whatever concentration we built into our initial sample, that will just have some Gibbs free energy, and there's no chance to lower that at all. Let's go down to a little bit lower temperature level. Let's say here we just barely begin to have this divot appear in the middle. So the temperature is lower now. This interaction term in green is more important. And so at this point we have a bit of concavity here. And just like we saw for the van der Waals gas, whenever we've got some concavity, then we can, bump that straight edge up against there and form a convex hull. So it's really small right here, but just cutting off that little bit of concavity means that we've got a division here. At this temperature line, we've got a left side, which is representing a homogeneous mixture that has a lot fewer A molecules than B's. We've got a region in between here that is actually a convex hull region. It's a line joining 2 points. So we've got a mixture, an inhomogeneous mixture between a pure liquid with the properties at that point and a pure liquid with the properties at this point. So we'll have one liquid that's rich in B and one liquid that's rich in A, and those will be separate from each other kind of like oil and water sitting together in the same jar but not mixing. So over here on our phase diagram, then we will have some separation line here, a mixture for that temperature. Let's go down to the next temperature then to see how this works out. So here we might have a really much bigger dip, a bigger divot in the middle. Still, we're always going to have these two points at the edge where it still dips down a little bit. So if we draw our line across there, then what we see is we've got a special point of contact there. So we've got one pure liquid at a really low concentration of A's, one pure liquid at a really high concentration of A's, and they are pure liquids if they're over to the left of this or over to the right of that, but in the middle it's going to be a mixture between two separate liquids. So we've got something more like that, where we got this mixture region in between. And then if I go on and draw the next one down here just really quickly, it might even be more steep. And you might not even be able to tell that there's these upticks right at the end. The concentration of the intersection between a line and the actual G versus X curve might be so close to 0 or so close to 1 you don't even notice. But it's still always there. And so the shape we get for this now is if we connect these, we only drew this for specific temperatures, but if we connect this, we form kind of an envelope here that looks something like that. So your normal mixtures of liquids, say if you mix, is a popular thing to mix, is maybe some juice, which is mostly water, and some alcohol, which might be a very large percentage of alcohol. But those things usually they mix together, right? They don't separate into bubbles. So that would be a system where we're still up here, right? We form one homogeneous mixture. But if you ever, mix some oil, like cooking oil, and some water, it doesn't mix up. It forms little bubbles. They float because they have different density. That would be a system that's much more like down here at a low temperature in this model, where we don't form we can set it up with any amount of oil and any amount of water we want, like 40-60. But when you do that, what you're going to end up with is a mixture of one part that's a lot oil and one part that's a lot water. And a few molecules may sneak into either side as you heat it up, but you still have two distinct things. So there's a couple of predictions from this then. If we mix two liquids and they're not mixable, they don't mix together, they stay separated, we must be in this phase mixture region here, and we might be able to get them to mix by heating it up, right? By heating it up, so if we started like here at some maybe a 40-60 mixture of 60% B's and 40% A's, as we can't change that. That's the amount of molecules that are in there. So if we heat it up, we're going on a vertical line up here. And what we see is, if our mixture may begin with two different liquids which are very distinct from each other, but as it gets hotter, say more water molecules can sneak into the oil, more oil molecules can sneak into the water part, and so now instead of forming a mixture which is like almost purely oil and almost purely water at the start, now we've got a mixture of some liquid which is like 10% water and 90% oil, plus a separate mixture that is 90% water and 10% oil. And as we keep going up in temperature, those two different liquids will become more, more mixed up with each other until we get to this point, and then at this transition, then the separation between the mixture disappears and they kind of just merge together. All right, so that's our mixing liquid model. And the takeaway from this is that what we do is we look at the, we look at the Gibbs free energy or another relevant energy. We plot that as a parameter is varied, and we look to see if there are any convex hulls that can be drawn on there. Convex hulls that can be drawn on there, and use those to construct a phase diagram. Where we're just sitting on a Gibbs energy line of a model, then we're in some pure state, because the state has that energy given by the equation. But if we're on one of these mixture lines, one of these convex hulls, then our real system will actually form a mixture, inhomogeneous, between two different states of matter, two different chemical states, one on the left contact point and one on the right contact point. Now that we've seen how to generate a phase diagram from a Gibbs free energy function, along with the concavity test, and if there is any possibility of having a convex hull line bridge across, let's look at the general types of phase diagrams that we could possibly encounter. Now, most mixtures of, say, a metal with two components as an alloy, or a solution of two liquids mixed with each other, or even a solution of salt and water, will have rather complicated phase diagrams, but they can always be made up of a few simple pieces. Let's see what those are. The first one we've already encountered in the van der Waals model. It's called a critical point. We also saw this one in the mixture of two liquids. A critical point is where the Gibbs free energy function develops a concavity naturally because of its formula over time, or over temperature. So at a high temperature, we have no concavity. At a medium temperature, we begin to generate some flatter region on the Gibbs free energy curve. At a low temperature, the Gibbs free energy curve may naturally develop a concavity. And when that happens, the concavity is bridged by a convex hull line, and that becomes a phase separation mixture region. So on our phase plot, for a critical point, we always see the same shape. We see a envelope that has a roughly parabolic shape at the top, and this represents the beginning of the mixture region. So we have, at high temperature, we have a homogeneous substance. As we lower the temperature, there becomes two distinct states, one at one composition, one at a different composition, and the system forms an inhomogeneous mixture of those two states. So what this means on the phase plot is if we, set up a mixture with a certain percentage of component A and a certain percentage of component B, then it must always live along this line. As we lower the temperature from way up high, it stays homogeneous until it reaches this boundary. And then what happens at this boundary is it splits into two different substances that are mixed together inhomogeneously. And the original mixture composition is retained. The overall fraction of A to B is retained, but instead the system does that by forming a mixture of two different liquids, one that's rich in B and one that's rich in A. So along these mixture lines, we can still apply the lever rule like we did for steam and water, just between a mixture with this percentage and a mixture with that percentage. Okay, so that's what a critical point looks like on a phase plot. We'll keep that in mind. I'll put it up here. Critical point has a bump shape, the beginning of a mixture region. The second type of behavior on a phase diagram that we might encounter is called an azeotrope. An azeotrope occurs when we have two different phases that each have their own function for a free energy. So we have something that looks like there are two curves for a free energy. How might we get these, you ask? Well, these curves can be attained by taking the matter that's present, assuming that it's in a solid state with a certain crystal structure, and deriving the free energy that that structure would have. It's beyond the scope of this course to figure out how to do that, but we would get a free energy curve which is sharply peaked, something like this. If we did the same thing for some matter in the liquid state, we would get something which is much flatter. So the shape of the azeotrope comes from the fact that this liquid curve will move down as temperature increases. It'll move down much faster as temperature increases than the solid curve because liquids have more entropy than solids. We could also apply this to a liquid and gas. So here is our high temperature, here is our low temperature, and our medium temperature curve is one that just goes right across this, so the lines are tangent to each other at this point. So let's think about what kind of shapes would result on a phase diagram from this competition of free energy options. Well, at high temperature, what we're going to see is 100% homogeneous liquid, right? At the medium temperature, we've got this one special point here. So at high temperature, we're all liquid. At medium temperature, we have this one special point right here. We can almost call this the Azeotropic Point. We'll see what significance this had us in a few seconds. If we look now at the low temperature, we'll see that what's happened is really in the azeotrope, one of these free energy curves kind of pierces through the other one as it moves. So at this other side here, we can form two convex hull lines, one, say, about there between the solid and the liquid on the right side, and a different one between the solid and the liquid on the left side. So we have a small window here where the solid can exist in a pure state, and then we have a large mixture region on each side and pure liquid beyond that. So down here at low temperature, what we've got is this kind of behavior where there is a region, a narrow region that is all solid. This region grows as the temperature drops because this liquid curve moves up. These tangents get pulled to steeper angles. And then we've got sort of a wide mixture region on either side. And anywhere outside this envelope is a 100% liquid. So we get this shape for an azeotrope, and the azeotropic point is right here. Now, what does this mean? Why is this interesting? Well, if you look at what's happening here, on this graph it's versus volume because I've kind of set this up as a Helmholtz energy. But if you set up your system at different volumes, right? Say you're at a volume here, then what you're going to encounter is a mixture of liquid, and then all liquid. So if you started at this point all liquid and you tried to cool, you would go down to a certain temperature here, and then you would start forming some solid, right? You have a mixture of liquid and solid. That's what's in this region. The mixture would be dependent on a lever rule between these two mixture sides. But if you were setting up a volume right here and you cooled from liquid, you would go straight down, you would almost immediately transition into solid. If you were right at this spot, you would go straight into solid. There would be no mixture time at all. So the azeotrope has the effect of basically raising or lowering the temperature that the phase transition occurs at. So if you're right at the azeotrope, you can get either the minimum or the maximum temperature of the phase transition, but if you're off to the side, you can change that. So here's the basic shape of an azeotrope. We've got one phase pure outside, one phase pure in the middle, and then two mixture regions on either side. This is often used to influence freezing or boiling points of mixtures. I believe in the textbook it references, say, antifreeze in water, or salt in water to try to alter that freezing point. Okay, so that's what an azeotrope looks like. And we'll move on to the next. The third type of behavior we might see on a phase diagram is called a eutectic point. To get a eutectic point, you really need to have three different possible phases for the system. Usually these are called an alpha type crystal, a beta type crystal, and a liquid curve. So these again would be usually found in discussions of metallurgy, where you're making an alloy with a certain composition of one metal versus another. And these would be then plots of the Gibbs free energy versus composition percentage. As temperature changes, the alpha and beta curves are not going to move very much because they have low entropy. The liquid line is going to move down because it has a higher entropy. So I'm not going to be so interested about what happens outside of these two alpha and beta curves. I'm going to be more interested in this eutectic point, and that happens when the liquid curve pierces the convex hull between the alpha and beta crystals. So what's that going to look like? Well, if I go up to a slightly higher temperature, I'm going to be able to get a convex hull between the alpha, or between the beta and the liquid, and between the alpha and the liquid. And I'll have a region in the middle which could be purely liquid. So in terms of temperature versus composition, this is what the eutectic point would look like. Initially we would just, at our low temperature, we would have a region of pure alpha, a region of alpha beta, inhomogeneous mixture of two different crystals, and a region to the far right of all pure beta type crystals. Right? Now, at some middle temperature here, this liquid line will just come down and become tangent to that convex hull, and it will break the convex hull in half. So we're going to have a point here at M where a liquid state suddenly appears. And as soon as that liquid state appears, the line that joined alpha and beta is destroyed. It's busted in half immediately. You've got this liquid appearing in the middle, and then the lines of convex hull, instead of going straight from alpha to beta, they have to go from alpha to liquid, and then from liquid to beta. So we don't just generate a liquid here, we also have a critical line. Because at this one temperature, below this temperature, there's a distinction. Alpha and beta is the crystal, and above this temperature, suddenly there's some liquid. So there's a distinction here between these. And what we get is a shape that basically looks like this. So over here on the left is our region where we can have all alpha structures for crystals. In the bottom middle, we have a mixture of two different solids, inhomogeneously mixed. In the center region here, we have the liquid state. And then between the alpha and the liquid, we have a mixture of some liquid, some homogeneous liquid, plus some alpha crystals floating around in it. On the other side, we've got some beta crystals floating around in the liquid. So that's what our eutectic point looks like. And the eutectic point is right here, this dot. So again, we can see the usefulness of this, looking at it in terms of really versus temperature, right? So the temperature that these different transitions occur at depends on what concentration of the alloy you make, right? If you make it too rich in beta, it's just going to be a solid with that crystal all the time. If you make it if you make it really high in the fraction X, then it's going to be this crystal all the time. If you make it low in fraction X, it might be alpha crystal all the time. But if you choose a specific ratio between the two parts of the alloy, some called the eutectic, this is called the eutectic composition, then what you get is the behavior versus temperature along this line. And that means that if we started with a liquid and tried to cool it, it would solidify at kind of the lowest temperature possible. So we can keep things liquid a lot longer by making them out of a eutectic composition. If we're melting mixtures, we can also make them melt earlier, right? So one of the things that you can do, with alloys of like copper and tin or copper and zinc, is you can play around with this mixture to get the exact melting temperature that you want. You might want it to be high, you might want it to be low. All right, so let's write that in as one of our other shapes, eutectic. It looks like a guy, doing the YMCA or something. All right, so like that. Okay. The last type of point that we can really see at all on phase diagrams is called a peritectic point. So again, we're in the context of having a mixture of two solids which might melt, and we have an alpha and a beta type crystal. And at low temperatures, we have a line joining them, alpha beta, convex hull. So this looks just like the eutectic did originally, but the difference here for the peritectic point is that you're going to be talking about a third phase here, gamma, which is going to lower down below alpha and beta as the temperature is raised. So here is high temperature and here is low temperature. Okay, so let's consider what would happen here. At low temperature, we've got alpha, we've got this mixture, convex hull mixture line there, we've got some beta, and then we're going to have another convex hull that we can draw over to gamma. So our phase diagram versus X versus temperature. At low temperature, we're going to have a region of alphas, a region of mixture between alpha and beta, a very narrow region of betas, beta. Then we're going to have a mixture region here between beta and gamma. And then off to the right, it's all gamma. All right, what about the high temperature? Well, in the high temperature, this gamma curve has moved down so much that a convex hull can be drawn now from there to there, and it sort of cuts off the beta curve completely. So at higher temperature, we would get a little bit of alpha region, then a mixture between alpha and gamma all the way over to here, where then we have all gamma to the right. So the critical point here for this type of behavior is really when this gamma curve comes down to be directly tangent to this alpha beta line. And at the instant that that happens, at that specific temperature, there's a line between all three peaks. Just below it, there's a possibility of some beta sneaking in there, right? And some mixture between beta and gamma. But as soon as this peak gamma, this gamma curve drops below, it sort of lifts this line off the beta peak and the beta disappears completely. So what we'll see here is a certain critical temperature where this beta peak just vanishes like that. And instantly, the alpha beta mixture that was there before turns into an alpha gamma mixture. So we've got a horizontal line here like that. And instantly at the same temperature, this beta gamma line that might have been there before gets lifted off into a purely alpha to gamma line. So these regions for alpha beta and the alpha beta region and the beta gamma region just disappear and turn instantly into an alpha gamma region. So if you look at this, it actually looks quite like an upside down eutectic point, and that's exactly basically what it is. So if you think about it, the eutectic point has the beta curve moving up or down, and the peritectic point has the gamma curve moving up or down. So peritectic will occur whenever one of the outside of the three curves moves up or down, and a eutectic will occur when the curve in the middle moves up or down. So that's basically the only shapes that you can get on a phase diagram of three materials. And it turns out, barring crazy circumstances where four of these things are tangent together, even in systems where there's four materials, crystal structures or more, you still only really see one of these four types of points. So a peritectic point then has this structure with the V on the bottom. Okay, so let's just go through in summary and label what's going on here. At the critical point, we have a mixture region in between, and then some homogeneous regions outside. At the azeotrope, we have one type of substance in between, pure. On the outside, we have a different type of substance, pure. And between them, we have a mixture. Two different places to have a mixture. At the eutectic point, we have a phase on the left, a phase on the right, a mixture between them in the bottom, and then at the eutectic point, suddenly a liquid appears. And these two arms hold mixtures of the different crystals and a liquid. And at a peritectic point, we have one structure to the left, one structure to the right. At higher temperatures, we can have a mixture between them. But as the temperature is lowered, then we suddenly see a new phase appear, a new crystal phase probably. That's called beta, and it sneaks in the middle there. Right, so alpha, beta, and beta, gamma are like the legs. Right. So I want to, just tell you that these are the four types of shapes you might see. I remind you that when you're in one of these pure regions, alpha, beta, gamma, or anything, you just have to know the pressure. You have to know the temperature and the composition percentage. It's going to vary continuously. But whenever you're in one of these mixture regions, you can use the lever rule between 2 points on the edges at the same temperature. Okay, let's look at some phase diagrams for realistic systems and see if we can identify this equation, this behavior. All right, so here's one that I generated on a computer, just qualitatively. It doesn't represent a real system, but it has this sort of peritectic / eutectic behavior going on. And you can see that there are some eutectic points and that there are some peritectic points. And you can see sort of how these are now pieced together in order to generate the entire phase diagram. Every place you look is going to have, every place the lines intersect, they're going to do so in one of these four ways. The second diagram that I'm showing up here is an alloy. It's an alloy of two metals based on their composition. And what you'll notice here is there are some points that are clearly eutectic, some points that are clearly peritectic, but there also appear to be some points that are just like vertical lines. And we don't have that up here. Well, in reality, when you have these peritectic and eutectic points, the region of beta, like here, can be extremely narrow. Remember, it was the region of beta was based off of the region between these two tangents touching here, right? And if this beta free energy curve is really sharply pointed, then that region can be super duper narrow. And so it usually is just drawn as a straight vertical line on the diagrams. Not really possible to nail that composition perfectly to get that crystal to show up. Okay, so let's look at another phase diagram here. Here's one that is kind of popular. This is the phase diagram for water or any solid liquid gas system. So we'll do it for water first. We'll do a PV phase diagram for water. All right, and for water, what it looks like is this. All right, and there's a little bit of weirdness in this region here, but we'll talk about that in a bit. So for water, generally we associate this part over here with the solid, this part over here is the gas, and this wedge area in the middle is the liquid. Here is a mixture of liquids and gas. This hump here is a critical point. On the bottom is a mixture of solids and gases. Across here is sublimation, and in the middle here is a liquid-solid mixture. I've drawn the dashes in here because what actually is going on for water is that there's kind of a discontinuity in this curve. The solid has a higher volume than the liquid, so we actually have to like kind of go underneath this. The phase transition goes back to the right, and then we're in the solid region. So there's like an overlap here. But what we can see here is it's a eutectic point, right? Right there is a eutectic point. We got solid and gas are the two phases on the outside, a solid gas transition in the middle on the bottom, and then the liquid suddenly appears. All right. So what we can know about this phase diagram is that we've got, a curve for solid. We've got a curve for gas that sits out there, and then at a certain temperature, there's a curve for liquid that breaks through these two things. That breaks through as temperature goes up. It pops into existence right there, and that forms our eutectic point. We usually call this the triple point for water and not the eutectic point. We call it the triple point for solid, liquid, gas systems, but it is the same underlying behavior in free energy curves as a eutectic point in a metal alloy. That's kind of cool.